Hello everyone, welcome back to the Data-Driven Hospital series. This is your first time joining us. I am Dr. Cliff. In this series, we are building a complete hospital information system from the ground up by exploring the intersection between healthcare, data analytics, database management, and health informatics. Over the past 2 episodes, we have laid a strong conceptual foundation. In episode 1, we explored what it truly means to be a data-driven hospital. We examined how healthcare organizations generate vast amounts of data every day, discuss the transformative role that data plays in improving patient outcomes, supporting clinical decision-making, optimizing operations, and driving hospital care. In episode 2, we shifted our focus to database design. Together, we developed the blueprint for the Northbridge Hospital Information System. We identified the key entities within our healthcare ecosystem, defined their attributes, and established key relationships that connect them to a scalable database infrastructure. However, a blueprint alone does not create a building. Likewise, a database design remains little more than an idea until it is translated into a functional system. This is exactly where today's episode begins. This marks a significant milestone in our journey. The first time in this series, we move beyond concepts and diagrams and begin the process of implementation. Today, we'll transform our database design into a living, functional database. We'll explore what MySQL is, why it has become one of the most widely adopted database management systems in the world, how to install and configure it, how to navigate the MySQL Workbench development environment, and ultimately how to begin constructing the Northbridge Hospital database using SQL. By the end of this episode, you will not only have a fully configured database environment on your computer, but you will also understand the fundamental principles that underpin modern database development. So without further ado, let's begin. Now that we have outlined what we'll be covering in this episode, let's begin with the technology that will power our entire hospital information system. At its core, MySQL is a relational database management system. In simple terms, it is a software designed to store, organize, and manage data efficiently. Think about the amount of information generated in a hospital every single day. Without a proper system to organize that information, managing it becomes increasingly difficult. MySQL solves that problem by allowing us to store data in structured tables and establish relationships between them. Instead of having scattered spreadsheets or disconnected records, we can create a centralized system where patients, staff, departments, consultations, laboratory investigations, and pharmacy transactions are all connected. This ability to organize and relate data is what makes a relational database so powerful. Now, MySQL is not the only database management system available. Other popular options include PostgreSQL, Microsoft SQL Server, Oracle Database, SQLite, and MariaDB. Each has its own strengths and areas of application. However, MySQL remains one of the most widely used database platforms in the world because it is reliable, powerful, open source, and relatively easy to learn. These qualities make it an excellent choice for our Northbridge Hospital project. So how do we get started? We need 2 main components. The first is MySQL Server. This is the actual database engine responsible for storing and managing our data behind the scenes. The second is MySQL Workbench. Workbench provides the graphical environment where you can write SQL code, create databases, manage tables, and interact with our server more easily. To install both, open your browser and search for MySQL Community Downloads. Download the MySQL installer from the official MySQL website and launch it. When prompted to choose a setup type, select Developer Default. This option includes MySQL Server, MySQL Workbench, and the tools required for database development. Continue through the installation wizard, and when asked to create a root password, choose one that you can remember because you will need it whenever you connect to your database server. Once the installation is complete, launch MySQL Workbench. If everything was installed successfully, you should see a local MySQL connection on the home screen. And that's it. You now have a professional database development environment installed and ready to use. At the very top of the MySQL Workbench window, you find the main menu and toolbars. These components provide quick access to the most frequently used actions. The main menu is positioned at the very top of the application. It contains standard options such as File, Edit, View, Query, Database, Server, and Help. From this menu, users can create new SQL files, open existing scripts, save work, manage database connections, access application settings, and customize display preferences. Think of the main menu as the master control center for the entire application. Directly below the main menu is the main toolbar. This toolbar provides shortcuts to commonly used actions. Examples include opening a new SQL tab, opening an existing SQL script, saving files, refreshing database objects, and switching interface layout. Instead of navigating through multiple menus, these buttons allow us to perform actions with a single click. As database developers, these shortcuts can significantly improve productivity. Located directly above the SQL editor is the Query toolbar. This is one of the most important toolbars in MySQL Workbench. Its primary purpose is to execute SQL commands. The main recognizable button is the lightning bolt icon, Execute. When clicked, MySQL sends the selected SQL statement to the database server and displays the result. Throughout this series, the lightning bolt button will become one of the most frequently used buttons. On the left side of the screen, we find the Navigator panel. This panel serves as the organizational hub of MySQL Workbench. It is divided into several sections. The Administration tab contains tools for managing the database server itself. Here we can monitor server performance, view active connections, manage user accounts, configure permissions, perform backups, and import and export data. Database administrators spend a significant amount of time working within this section. As our hospital system grows, these tools will become increasingly important. The Schemas tab is where we spend most of our time. A schema represents a database and all of its objects. Inside each schema, we can view the tables, views, stored procedures, functions, and triggers. For example, after creating a hospital database, expanding the schema will allow us to see tables such as the patients, the staff, the departments, the admissions, and the visits. This section gives us a visual representation of the database structure we create using SQL. At the bottom of the navigation panel is the information area. Whenever we select a database object, this section displays useful metadata. For example, selecting a table may reveal column names, database types, constraints, and storage information. This feature provides a quick way to inspect database objects without writing additional SQL commands. At the center of MySQL Workbench is the SQL Query Editor. This is where database development truly happens. Just like a web browser, MySQL Workbench supports multiple tabs. Each tab can contain a separate SQL script. This allows us to work on multiple projects simultaneously, organize different queries, compare scripts side by side. The code editor is the primary workspace. This is where we write SQL commands. As we begin typing, MySQL Workbench suggests table names, column names, and SQL keywords. This feature reduces typing effort and improves accuracy. The editor continuously analyzes our code. Potential mistakes are highlighted before execution. This helps developers identify problems early. Think of it as having a built-in assistant reviewing your SQL statements as you write them. Once SQL commands are executed, MySQL Workbench displays the results in dedicated panels. These panels provide immediate feedback about what happened. After running a select query, the retrieved data appears in the result grid. The result grid displays the data in rows and columns similar to a spreadsheet. Users can browse records, sort data, filter results, and edit values directly. This makes data exploration simple and intuitive. Adjacent to the result grid is the form editor. Rather than displaying information in a table format, it presents each record as a structured form. This is particularly useful when tables contain many columns, large text fields, and clinical notes. The form editor makes individual record editing much easier. Located at the bottom of the application is the Action Output panel. This panel records every action performed during the session. Information displayed includes executed SQL commands, execution time, success messages, error messages, and warnings. Whenever a query fails, the action output panel is often the first place to investigate. It serves as a running activity log for the database session. The first thing any database project needs is a database, so let's create one. This command is an example of what we call a data definition language, or a DDL. Remember, DDL commands are used whenever we want to define the structure of a database. We are not inserting patient data yet. We are not querying data. We are simply building the framework that will eventually hold the information. The create keyword tells MySQL we want to create something new. Database tells MySQL what we are creating, and node bridge becomes the name of our database. Once executed, we have an empty database waiting to be populated. Next, we need to tell MySQL that this is the database we will be working in. Think of this as opening the hospital building before we start furnishing the rooms. Everything we create from this point onward will be stored inside the node bridge database. Now let's begin creating the tables. And naturally, we start with the patients, because without patients, there is no hospital. When designing a hospital database, one of the first questions we ask is, what information do we need to identify and contact the patient? That's exactly what this table captures. The first column is the patient ID. Notice we use the integer data type because identifiers are whole numbers. Also, we specify the not null constraint. This means every patient record must have an identifier. The auto increment keyword is particularly important. Instead of manually assigning patient numbers, MySQL automatically generates them. The first patient receives the ID 1, second patient receives the ID 2, and the third patient receives the ID 3. At the bottom of the table, we define the primary key, which is the patient ID. The primary key uniquely identifies every record in the table. No two patients can ever have the same patient ID, and this is one of the most important concepts in relational databases. Moving down, we have the first name varchar 50 and the last name varchar 50. Varchar is used because names vary in length. The number 50 indicates the maximum number of characters that can be stored. Notice these fields are also marked not null. A hospital record without the patient's name will be difficult to use clinically. We then encounter the date of birth with a date data type. The date data type stores calendar dates only. This is appropriate because we do not need the exact time a patient was born for routine hospital operations. Further down, we see the phone varchar 20 and the email varchar 100. These fields support communication and follow-up. Notice that the maximum lengths differ because email addresses are typically longer than phone numbers. The address and occupation fields use the text data type. Unlike varchar, text is designed for larger and less predictable amounts of information. The patient's address may be short or extremely detailed depending on the context. At this point, we have successfully built the foundation of our entire hospital information system. Every other table we create will somehow relate back to patients. Before creating staff, we need departments. After all, doctors and nurses belong to departments, laboratory scientists belong to departments, and pharmacists belong to departments. So let's create them. This is intentionally a simple table. Every department receives a unique identifier and a department name. Examples might include internal medicine, pediatrics, surgery, laboratory, and pharmacy. Notice again the use of the auto increment and primary key. These design patterns appear repeatedly because every table requires a reliable way to uniquely identify its records. Now we can create the hospital staff. This table introduces one of the most powerful features of relational databases, the foreign key. Notice the column the department ID with the integer data type, and later foreign key of department ID, referencing the department's ID on the department's table. This creates a relationship between staff and departments. A doctor cannot belong to a department that does not exist. Similarly, a nurse cannot be assigned to an invalid department. Therefore, the database itself enforces these rules and this is what protects data quality. Instead of relying on individuals to remember relationships, the database enforces them automatically. Now we reach the heart of clinical care, the outpatient consultation. This table captures what happens during a patient encounter. Immediately, we see the patient ID integer not null, the visit date time not null. Unlike the date data type, date time stores both the date and the exact time. In clinical practice, timing matters. The vital signs section introduces another data type. Decimal is used whenever numerical precision is important, for example, a temperature of 38.5 degrees Celsius. Unlike floating point numbers, decimal preserves accuracy. This is particularly important in healthcare. As we continue throughout the table, we encounter several text fields such as a presenting complaint, issue of presenting complaint, review of systems, physical examination, diagnosis, and the management plan. These are all narrative clinical notes. Their length can vary tremendously from one patient to another, making text the most appropriate data type. At the bottom, we establish two key relationships. One links the visit to the patient, and the other links the visit to the doctor. This effectively answers two important questions: who was seen and who saw them. The remaining tables follow the same philosophy. Laboratory visits link investigations back to patients, requesting physicians and departments. Pharmacy visits connect dispensed medications to patients, prescribers, and pharmacy services. Admissions capture inpatient episodes, linking patients to departments, beds, diagnosis, and attending staff. Follow-up visits preserve continuity of care by documenting what happens after the initial consultation.